Welcome to the deep dive. Today, we're jumping into system design concepts.
Yeah, the big ideas behind the tech we use constantly.
Exactly. We're aiming to pull out the core stuff, give you a solid foundation without getting totally lost in the technical jargon.
Right, because system design, it's really about thinking at scale, understanding the choices you make.
It really is relevant for almost anyone in tech, isn't it?
Definitely. It's that big picture thinking.
Okay, so let's start with basics. A system suddenly gets popular, tons of users. How does it handle that? That scalability, yeah.
That's the one. And there are two main ways, really. Scaling up.
Like getting a bigger computer.
Precisely. More RAM, faster CPU, but that only gets you so far.
And the other way, scaling out.
Yeah, scaling out is adding more machines, distributing the load. That's how the really big systems work. Horizontal scaling, they call it.
Got it. More machines working together. Makes sense. But being big isn't enough if the system keeps falling over.
Yeah, definitely not. That leads us to availability and reliability.
Okay, what's the difference there? They sound kind of similar.
They're related, for sure. Availability is just, is it up? Can users access it? Often measured in those nines, like 99.99% uptime.
Right, the percentage of time it's actually working.
And reliability is more about it working correctly when it is up.
Yeah.
Consistently. No errors, no weird behavior. You need reliability for high availability.
Okay, so available and trustworthy. Now, speed. Nobody likes a slow website or app. Latency and performance.
Latency is that delay, right?
Yeah.
The time between your request and getting a response. Performance is the overall picture, how efficiently things run.
And we can improve that with things like caching.
Caching is huge, yeah.
Yeah.
Storing common data closer so you don't have to fetch it from far away every time. Optimizing code helps too, of course.
Yeah.
Better user experience is the goal.
Makes sense. All right, let's shift gears to data. Managing data across lots of machines. Consistency models. Strong versus eventual.
Yes. This is a big
Yeah.
trade-off. Strong consistency means everyone sees the exact same data, instantly updated. Think banking, you need that.
Can't have different balances showing up.
Exactly. Eventual consistency, though, allows for a small delay. Your data will eventually be consistent everywhere, but maybe not instantaneously.
Like social media. And like showing up a second later isn't the end of the world.
Precisely. It lets systems scale massively and stay highly available, even if there's a tiny lag in updates sometimes.
Okay, that trade-off makes sense. And that connects to the CAP theorem, doesn't it?
It does, directly. CAP theorem basically says for distributed data stores, you can only perfectly guarantee 2 out of 3 things: consistency, availability, and partition tolerance.
Partition tolerance meaning it still works even if the network splits.
Right, which happens all the time in large systems. So you pretty much have to have partition tolerance.
Which means you're forced to choose between strong consistency or high availability.
That's the core choice. CP systems prioritize consistency, AP systems prioritize availability.
Fascinating fundamental constraint. Okay, storage itself.
Yep.
SQL versus NoSQL. Quick take.
SQL structured data, predefined schema, like spreadsheets. Great for complex queries, guarantees like ACID. Think financial transactions.
The traditional databases most people know.
Yeah. NoSQL. More flexible, often no fixed schema. Built for scale and flexibility. Think user profiles, IoT data. Often follows base properties instead of ACID.
So different tools for different data shapes and needs. Sometimes you use both.
Absolutely. That's called polyglot persistence. Use the best database for each specific job.
Right tool, right job. Okay, databases get huge. How do we split them up? Sharding and replication.
So sharding, or partitioning, splits the data horizontally. Puts different rows on different servers based on some key, like splitting a giant phone book by last name initial.
Spreads the load, speeds things up.
Exactly. Replication is about making copies. You have a primary database and replicas. Reads can go to the replicas, take a load off the primary, and if the primary fails.
A replica can take over, fail over.
Correct. Improves read performance and resilience.
Split and copy. Got it. Now, managing incoming traffic. Load balancing seems vital.
Oh, absolutely essential. A load balancer sits in front of your servers and distributes incoming requests, like a traffic cop.
Prevents any one server from getting swamped.
Yep, boosts availability, helps with scaling, improves performance. Can work at different network layers too, like layer 4 or layer 7.
Okay. Smooths out the traffic flow. And for speed again, caching, we mentioned it, but what types are there?
Lots of places to cache. client-side in the browser, CDNs, which are global caches,
We'll get to CDNs in a sec.
right? Then server-side caching, maybe in memory, or using dedicated distributed cache systems like Redis or Memcached
All about keeping copies of data close by.
to avoid hitting the slower main data source constantly.
So CDNs, content delivery networks, how do they specifically cut latency?
Think of them as a network of servers spread across the globe. They store copies of your static files, images, videos, CSS.
So when I visit a site,
You download those files from a CDN server geographically close to you, not from the original server maybe halfway across the world. Much faster.
global shortcuts. Nice. How do system components talk? API design.
APIs are the contracts between services. REST is super common stateless, uses standard HTTP methods. GraphQL is another approach, lets the client ask for exactly the data it needs.
Clear interfaces are key. What about tasks that don't need an immediate response? Message queues.
Perfect for that. Asynchronous communication. Service A drops a message onto a queue, service B picks it up later when it's ready. Decouple services handles load spikes.
Like sending a task off to be done in the background.
Exactly. Think RabbitMQ or Kafka.
Okay. What if a network glitch causes a request to be sent twice? Idempotency.
Yes, super important. An idempotent operation means doing it once has the same result as doing it 10 times. Think deleting a specific item.
Delete it once, it's gone. Try to delete it again, it's still gone. No harm done.
Right. Get, put, pet, delete requests are often idempotent. Post usually isn't. You might create 2 items instead of 1 if you retry. Critical for reliable systems.
Good safety net. How do we watch these complex builds? Monitoring and alerting.
You have to. Monitoring tracks everything: CPU, memory, application response times, error rates, even business metrics. Alerting tells you when something's wrong before users complain loudly.
Proactive problem finding. And obviously security. What are the absolute basics?
Non-negotiable. Authentication, who are you? Authorization, what can you do? Encryption, protect data in transit and at rest. Validate all input, rate limiting. Defense in depth is the philosophy.
Multiple layers of protection, and rate limiting helps stop abuse.
Yeah, prevents denial of service attacks, stops one user hogging resources, limits requests per IP per user per API key, etc.
Essential resource management. Okay, nearly there. Proxies, forward versus reverse.
Quick one. Forward proxy acts for the client, like in a company network. Reverse proxy acts for the server, common for load balancing, security, caching. Think in Jinx or HA proxy.
Client shield versus server shield. And finally, the absolute bedrock, networking basics.
Can't forget DNS, domain named IP address,
Yeah.
TCP/IP, reliable data delivery over the network, and HTTP, HTTPS, the language of the web. It all runs on this.
Wow. Okay, that was a whirlwind tour of system design. It really hammers home that it's all about trade-offs, isn't it?
Absolutely. There's rarely one right answer, just the best answer for specific needs and constraints. Understanding the why is key.
So thinking about all these interconnected parts, here's something to chew on. What single point of failure do you think gets overlooked most often in today's complex distributed systems? Something to ponder. Thanks for this deep dive.